Scientists aboard the M3 lab were completely baffled by this ridiculous system of differential equations. We can rewrite these by thinking to ourselves that we have a first derivative here, so we'll just call it d, and then we'll take the first derivative of x, and then we'll go ahead and subtract 4x, and then here we'll call this the d squared as if it was the second derivative of y, just an operation here, and we'll call that t squared. On this bottom side, we'll rewrite this as dx, the first derivative of x, plus the first derivative of y, and that's be equal to 0. Well, let's rewrite this one more way. We'll just say that d minus 4, we'll put parentheses there, call that x, and then we have plus d squared y equals t squared, and over here we have something like d plus 1, parentheses x, plus the dy equals 0. Now we see we have a system of equations here that we might want to get rid of one of these. So I'm going to try to get rid of these guys. I'll multiply this bottom thing by d, and then if we do that, then over here we'll get something like this. We'll get d minus 4 times the x, and then we're going to just subtract d times the d plus 1 with the x, and then these things are going to cancel, and then we just have that equal to t squared minus 0 is t squared. This, we could pull out our x's and we'll have that d minus 4 parentheses, and we'll have sort of a d squared plus a d, and then we'll pull out all the x's, call that equal to t squared. We can see that the d minus d is going to cancel. We have negative d squared minus 4 equals t squared, and we'll just call that d squared plus 4 being equal to negative t squared. But let's also realize that what this is saying is we have the second derivative of x plus 4 times x equals negative t squared. And we could recognize that we could solve this using an auxiliary equation. So like m squared plus 4 equals 0, and then we'll deal with the particular in just a second. But if we have m squared plus 4 equals 0, we'll get that m1 is equal to 2i, m2 is equal to negative 2i, and that will lead us to an x1 and an x2 of e to the 2i and e to the negative 2i, which we can simplify down and it'll become cosine of 2t. Oh, I forget the t here. And this will become sine of 2t. These little things I forget, like the x is here and the t's there. Well, this will just lead us into the homogeneous solution of being c1 cosine of the 2t plus c2 sine of 2t. Now let's say we wanted to figure out what the x particular was. X particular is just going to be in the form of this t squared, so at squared plus bt plus c, and then we'll have to take the first derivative, so x prime is going to be 2at plus b, and we'll take the second derivative, so that'll just be 2a. That's all the derivatives we need here. We're just going to plug this right into there, and so we'll get something like the second derivative is 2a plus, and we need 4 times this one, so 4 times this is going to be 4at squared plus 4bt plus 4c. That's going to be equal to negative t squared. And here's where I'll jump through the math, and I'll basically just say that a equals negative 1/4, b is going to be equal to 0, and c is equal to 1/8, giving us the particular solution of negative 1/4 t squared plus 1/8. That means that now we have a solution for x. We'll call x being equal to c1 cosine of 2t plus c2 sine of 2t minus 1/4 t squared plus 1/8. And that's simply because we have the homogeneous plus the particular. So we're just going to basically add this and that, and we get the entire x. Now let's solve for the y's. So in order to solve for y's, we have to multiply, we have to get rid of these guys. We'll multiply this by d plus 1 and this one by d minus 4. So when we do that, we're going to get something like d squared y with a d plus 1 on top. And then we'll subtract this guy, which is going to have like a dy and then a d minus 4. And that is supposed to be equal to this t squared times a d plus 1. T squared d plus 1 minus 0. We can do some sort of simplification here on the y side. We'll just basically be left with, we have a d to the third plus d here, the y. And then we have minus d squared minus 4d. And here's another y. And then we have that being equal to, well, this is actually just acting on this t squared. So it's derivative of t squared, so 2t. And then over here we have plus t squared. Let's not forget there's actually 8d squared there. Well, essentially we're going to pull this out, and we have d to the third plus d squared minus the d squared minus 4d, and then there's a big y in front of it, and that's going to be equal to the 2t plus t squared. So this d squareds will cancel, and we're going to be left with the d to the third minus 4d y equals 2t plus t squared, and we can translate this into maybe something a little bit more familiar. So d to the third y over dt minus 4 dy over dt equals 2t plus t squared. And we can recognize the auxiliary equation. This one is going to be m to the third minus 4m, which equals 0 for the homogeneous. We got the particular lined up here. But with this equation, we know that we have an m1 being equal to 0, an m2 being equal to 2i, and m3 being equal to negative 2i, which will lead us into a y1, a y2, and a y3. Here is e to the 0, this one is e to the 2i, and this one is e to the negative 2i, which will become 1 cosine of 2t. Let's not forget that t there. And this will become sine of 2t. We have similar answers. But when we set up our y homogeneous equation, this guy right here is going to be just a constant c4. Then we have plus c5 cosine of 2t and c6 sine of 2t. Here's where things get a little bit weird, because if we wanted to find the y particular of this, we think that it would be the t squared. Okay, so let's put a t squared plus bt plus c. But then we come into a problem, because now we have this constant and this constant, and remember that we can't have repeated solutions. So since we already have a constant in our homogeneous equation, this guy has to be a constant times t. So we actually have to add in a t there in order to get that repeated solution going, which is sort of what we have to do here as well. So t to the t squared, and then a t to the third over here. So we essentially raised up our particular solution by a factor of t, because the homogeneous already simply has the constant. So there's no plus d right here, no constant in the particular solution. Now we can start taking our derivatives. Y prime here is going to be 3at squared plus 2bt plus c. And we need to get to y prime of the third derivative. So double prime gives us 6at plus 2b, and triple prime gives us 6a. Now we have to plug these guys back into this equation. So we have something like 6a, and we have minus 4 times the first derivative, which is this one. So we have minus 12at squared. Then we have minus 8bt, and we have minus 4c, and that's going to be equal to the 2t plus t squared. And here I'll skip through all the math. I'll say a is supposed to be equal to 1/12, b is supposed to be equal to 1/4, and c is going to be negative 1/8. So now we were able to find our particular y. I'll put the y particular here. The particular y is supposed to be 1/12 t to the third plus 1/4 t squared minus 1/8 t. And combining the y particular with the y homogeneous, we get a y being equal to, we have c4 plus c5 cosine 2t plus c6 sine 2t. plus 1/12 t to the third plus 1/4 t squared minus 1/8 t. But here's the thing, we're not done yet. We have too many constants, C1, C4, C5, C6. We have to get rid of those somehow. Well, let's turn our attention to this equation right here. It says that the first derivative of x plus the first derivative of y equals 0. So let's see if we can combine these and get something going here. It turns out that the first derivative of x, let's start doing that over here. And let's ignore these constants because all this stuff over here isn't going to have an impact on the C1s, C5s, and whatever. So we'll just focus on taking derivatives of these things. We get something like negative 2 C1 sine of 2t for that first bit. And then we have a plus 2 C2 cosine of 2t for the second bit. This is dx. We'll know that x is supposed to be equal to, we'll just put C1 cosine of 2t plus C2 sine of 2t. And then we'll have the dy is going to be equal to just this stuff right here. We get a negative 2 C5 sine of 2t. And then we have plus 2 C6 cosine of 2t. If we try to add this all up, it's supposed to be equal to 0. So let's combine the cosine terms. We have 1, 2, 3 cosine terms. We'll get that 2c2 plus c1 plus 2c6 equals 0. Or there's really, I can multiply this by the cosine here. Cosine of 2t, which equals 0. But clearly, then we'll just make this equal to 0. So we get just this equals 0. We do that thing for the sine as well. So we'll add up the sines. We'll have negative 2c1 plus c2 minus 2c5. Here's the sine of 2t. That's supposed to be equal to 0. Let's try to get rid of the bigger c's here. So we're just going to drop down everything over here. We're going to get something like 2c6 is equal to negative c1 minus 2c2, giving us that c6 is supposed to be equal to negative 1/2 c1 minus c2. And we could do the same thing for c5. So negative 2c5 equals negative c2 plus 2c1. And so c5 is supposed to be equal to 1/2 c2 minus c1. Now we could take these and replace it into this particular spot. So that will give us some answer that we can write down here. So we'll finally say that for x, that's going to be equal to, well, we didn't change any of these c1s or c2s. So we'll have x equals c1 cosine 2t plus c2 sine of 2t minus 1/4 t squared plus 1/8. That's going to be x. And for y, that's going to be equal to, we'll leave the c4 because we didn't get rid of that. But then we have plus c5, and we know c5 is equal to this. We'll just say 1/2 c2 minus c1. And then we have the cosine of 2t. And we have c6, so we'll just say negative 1/2 c1 minus c2. We have sine of 2t. And then we have 1/12 t to the third, 1/4 t squared, and this is minus 1/8 t, minus 1/8 t. Okay, so we have our two answers here, and that was pretty ridiculous.